restrict to the North Pole and the South Pole. We have a polynomial at each. And the fact is that something is in the image of this map, so we can figure out what the image is. It's in the image exactly if this polynomial and this polynomial, polynomials in one variable, they have the same constant term. So if their difference is divisible by x. And this isn't hard to show. There are a couple ways to do it, but that's what the fact is. And one of the few big theorems in here is that under certain hypotheses, so if you have isolated points, and there's several ways to say this, but if you have an additional criterion that guarantees that you have this sort of curled necklace of two spheres floating around in your manifold, then in order to figure out what the image of this map is, you just need to look at every curl in the manifold and look at the thing at the North Pole and the South Pole, look at the difference and make sure it's divisible by something. Okay, so this becomes quickly some very combinatorial or algebraic, generic algebraic calculation. And so examples, if we're in the case of applied variety things, polynomials will look like this. And for our Graphonian, we already have something like this. And there have been a lot of people who have used this to say some things. And of course, you can't read that, but I'll tell you a little bit about one of these papers. Okay, so this paper that I worked on as a postdoc talks about generalizing this result to, say, spaces even like loop spaces in a Lie group. So this GKM description works, even in infinite dimensional cases. It works for equivariant cohomology that we already knew. Sometimes works over Z if you're a little careful. It works in K-theory, and here I mean topological K-theory. In some cases, disagrees with operational K-theory if you're looking at it from the algebraic side, which agrees with algebraic K-theory for nice classes. And this equivariant K-theory description, say for loop spaces, was known already by Kaufman and Kumar in the 80s. And then it's also known in equivariant cobordism. And of course, these examples are only really, these computations are only really useful if you know what the equivariant theory of a point is. And here we do, and here we do, here we don't. Well, we do, but we can't really compute. So this is a theoretical theorem that's what is true is that we understand Euler classes, and that's what you need to understand really the image, but it's maybe of questionable use, but I should denigrate my theorems, I guess. Okay, in any case, this has sort of further applications and further thoughts. In Schubert calculus, this has been used by various people to think about different ways of doing Schubert calculus. I had hopes that this would lead to sort of easier combinatorics, but as far as I know, it hasn't yet. And it does, in theory, these are all just commutative algebra questions now, so you want to just program them in Macaulay 2 or something like that. But Macaulay 2 really likes quotient rings, and it really hates subrings. So it's very annoying. And if anybody has advice about how to ask questions about subrings, I would love to know. You can do some calculations of Gromov-Witten invariance and quantum corrections. You have to be careful what you mean by quantum corrections or what you mean by equivariant quantum blah, blah, blah. But there are possible ways to do this, and I'll say a little bit about this towards the end. And this has also come up in work of Masuda, Panov, Puck, when they were studying something called torus manifolds. This is now in a very topological category. So far, almost everything could be a projective variety, and so it's not saying very much, but theorems like this are true in a more topological context. And actually, one of the things I'm working on this semester with Henri Piresh is studying toric origami manifolds. What those are, they're a class of something called folded symplectic manifolds. And folded symplectic manifolds, it's another geometry defined by a differential form, and in that case, the differential form, the existence of a differential form is equivalent to existence of stable complex structures. So again, this gets into sort of very topological direction, the kinds of questions you ask. There is, in certain cases, we have some sort of GKM theorem, but in other cases, the fundamental group isn't zero. The spaces aren't simply connected. The fundamental group is not like the fundamental group of an algebraic variety. So algebraic varieties, I guess, have to have fundamental groups with even rank, and that's not true here. You can have S1 plus S3, and so you have fundamental group Z. And the big question, of course, maybe is topologically, can you determine the manifold combinatorially with some combinatorics up to cobordism? Okay. I am apparently talking very fast because usually I don't get to this point by half an hour in. Okay, so any questions? Okay. So in the last part of the talk, I wanted to say something about symplectic reduction and how these localization techniques can be used to say something about symplectic reductions. So symplectic reduction is the way of constructing quotients, constructing new examples for old ones in symplectic geometry. We have this momentum map, and in the symplectic category, you can use this to prove a lot of the results that I talked about already. And essentially, the reason is that this peak C, these individual functions behave like Morse functions. They're Morse functions in the sense of bot, which just means that they maybe don't have isolated critical points, but they're good enough. Oh, right. And I was supposed to mention, of course, it's celebrated, right, that Morse was here and developed Morse theory here, except that I was at Cornell recently, and my chair reminded me that, in fact, Morse was at Cornell before he was here, and the very beginnings of his of Morse theory were developed there, but okay. Okay, so the reason this momentum map is useful is that you can do Morse theory. It's also an equivariant map, and so that means that this level set, phi inverse of mu, any level set, is a T invariant submanifold. And if mu is a regular value, this is just differential topology, the level set is a submanifold. Okay, so you might say, well, we've got a symplectic submanifold of our original manifold, and of course, no, it's by differential topology, the level set is dimension m minus dimension t, and we know manifolds, symplectic manifolds are supposed to be even dimensional, but the miracle that happens is that I can restrict the 2 form to the submanifold, and the directions where it's degenerate are exactly the orbit directions for this T action. And so if I quotient out, this thing is even dimensional, and the theorem is that this quotient phi inverse of mu mod T is a symplectic space, and it has at worst orbital singularities. Okay, so this is the way to construct new examples. The basic example is this. Look at the circle acting on Cn by just scaling each coordinate. So that's my action. My momentum map for this action just takes a string of n complex numbers to the sum of the lengths. The level set at mu, this is just going to be a 2n minus 1 sphere, and the circle acts on this in the circle directions, that's just a Hopf vibration. So the quotient is just Cpn minus 1. Okay, so that's a very explicit way to see Cpn minus 1 is symplectic. And Del-Hotz's theorem says that compact toric symplectic manifolds are in one-to-one correspondence with some adjectives applied to convex polytopes. And the way he proves the existence part of his theorem, given a polytope, there is a symplectic manifold, is he says, well, okay, given the polytope, here's a way to take an affine space, where n is the number of facets in the polytope, divided by a torus that is of the appropriate dimension, to get a symplectic manifold. It has a residual, so let the Tn really acts here, and so there's a residual Tn minus d action on this, and this is the moment polytope for that residual action. Okay, and the combinatorics all works out very nicely. I should say the GKM theorem applies here, that the condition that all of these checking for each edge, all of these divisibility conditions, is equivalent to checking that an assignment of polynomials on a fan is a global piecewise polynomial. So there's been a lot of combinatorial work done on the ring of piecewise polynomials on a fan, and that's in some way just a reinterpretation of the GKM theorem. And so we can one might hope to understand that combinatorics a little better. Some more examples of quotients. If I have, let's see, so I have a Tn action on a flag variety, on Grassmannians, on cojoint orbits, or homogeneous spaces in general. These quotients are called weight varieties because depending on the symplectic form that you choose on these, and depending on the regular value where you reduce, this tells you something about weights of the torus action of a G action on a so if you think of a G rep, how do you break it up as a T rep in terms of your reducible representations? And so these are called weight varieties because there's there's a deep connection between these quotients and the corresponding representation theory. Okay, so another example, I said that we would see this as symplectic. It's symplectic because, well, we have this description. We have n vectors in R3. They're supposed to have length AI, so that says that we're living in a product of two spheres. This adding up to 0, it turns out, is just a momentum map condition. That's taking a level set at 0, and then we're dividing out by SO3. And so this is a symplectic quotient, and it fits nicely into the Gelfand-McPherson correspondence, so we can think of this product of S2s as a quotient of C2 to the n, and I quotient by torus, and then by SO3, I can alternatively quotient by U2 and hit the Grassmannian on the other way around of the diamond, and think of polygons as a quotient of a Grassmannian. So depending on how you want to think about your polygons, or depending on the kind of geometric calculation you want to do, torus quotients are sometimes easier, and this space we understand pretty well, like this space. So, okay, so cohomology of symplectic reductions. Francis Kerwin showed in the 80s that if we have a compact Hamiltonian T-space, then, so we know that the inclusion of the level set is an equivariance map, because this is an invariant subspace, so we get a map the other way. Francis Kerwin showed that this is a surjection, and of course the point is that when mu is a regular value, this is precisely the cohomology of the quotient. Okay, there might have been finite stabilizers, I don't want to worry too much about that, just call this what you want the cohomology of the orbital to be. Okay, this is possibly an orbital, and this is its cohomology. Okay, this works sometimes over Z. This is maybe not the best theorem you could prove, but it's sort of the first theorem you would prove, that in certain cases you still get surjectivity over Z. This is much fussier than the injectivity theorem being injective over Z. The technique for both of these theorems is that this, so for the localization theorem we were just doing Morse theory basically. Here we're doing something called Morse-Kerlin theory. This map, norm square of phi, that's a map from M to R. The minimum is 0 because we're just looking at norm square, and so the minimum, if the minimum critical set is phi inverse of 0, which is exactly a level set of our moment map, and then the idea is that you have some control of what the other critical sets are, and it's messy. It's not the original definition in Kerwin's work doesn't even make it look like it's a sort of differential topology kind of thing. It looks like you have some global condition. It turns out that this minimal degeneracy is something that you can prove locally, but even proving that is really fussy. You have to be very careful when you're doing your differential topology, but it is. And the other fact is that this kernel is computable. It was first computed, the kernel, in terms of in various ways using residues. Lisa Jeffrey and Francis Kerwin computed the kernel, but you can also compute it in terms of localization. Remember, we know this in terms of fixed points, and Sue Tolman and Jonathan Weitzman first showed, and Rebecca Golden defined, that you can describe this in terms of localization. And what I mean by that, so their theorem says something like, the kernel is generated by classes. If I'm taking a level set here, I look at all hyperplanes through my regular value, and I look at the classes that are supported on one side or the other of a hyperplane. If it's supported on one side or the other, I throw it in the kernel. If it's not, I don't, and then I take the span. And this is it's not obvious. There is an effective algorithm to compute this. I mean, this is not, it seems like you could be doing something horrible, but you're not. Okay, so the algebra of this is relatively easy to understand. And so that, or I should say, that already allows us to completely describe the cohomology of the quotient, at least if we know equivariant cohomology upstairs, which I hope I convinced you that we do. For toric varieties, if you do this, remember, toric variety is a quotient of an affine space. So for toric varieties, this gives you the description of the cohomology as a quotient of a polynomial ring divided by turns out the monomials, and that's the presentation, the Stanley-Riester presentation of the cohomology of a toric variety as a phase ring. Or maybe that's the Danilov-Jerkovich theorem. I'm always confused. In any case, it's the phase ring description. And the theorem that I want to end with, gosh, I'm ending very early. The theorem that I want to end with, but I guess it's all better to end early than late, the theorem that I want to end with is this. So if the quotient is an orbifold, toric varieties are usually manifolds, sometimes orbifolds. But if we're in the orbifold setting, then it turns out we can compute. So already Kirwan's theorem plus these kernel calculations tells us we can compute the regular cohomology. If in the orbifold setting, there are more refined invariants. So there's something called Chen-Ran cohomology, which is it's the degree 0 sort of stacky Gromov-Witten invariance of your orbifold. And with Rebecca Golden and Alec Knudsen, we showed that there is a surjection. This thing is big. I'm taking a direct sum over all of the elements of the torus. So that's not something you would normally do. Our macro for that in our text paper was \ROUS, ring of unusual size. And so this is maybe not something that's effectively computable, but it turns out that there's always a finite subgroup of T that you can use rather than using the whole torus. So this isn't as bad as it looks. And the kernel is very computable, exactly as it was for Tolman, Weitzman, and Golden. So everything in terms of localization, this becomes a very simple calculation. And it applies to symplectic toric orbifolds. It applies to weight varieties. And it can be generalized to equivariant K theory, where there's something to prove that there's a surjection in K theory. That is work of Megumi Hirata and Greg Landweber. But then the same kinds of techniques apply to stringy K theory, I think it's called, for orbifolds. You can do explicit computations in K theory. And Gonzalez, Woodward, Zillner, and a number of other people have been trying to understand the relationship between something you might call equivariant quantum cohomology of some space and the quantum cohomology of the quotient. And with Linda Chen and Kaisa Tekle, I've been trying to understand, or this semester I'm trying to understand what the quantum cohomology of these polygon spaces should be. At least in some nice cases, these are Fano varieties. So these are the kinds of generalizations. And I was supposed to say something else. Oh, right. So in theory, of course, one actually wants to do this for cobordism because you know how to compute some kind of cobordism. But as I said, equivariant cobordism of a point is I don't know how to make norm square of the normal map into a nice function with regard to cobordism, equivariant cobordism. So that seems hard. Thank you very much. near the boundary. Then you define the saucer D to be, say so D is subset of, D is subset of to be W, V, and D times R such that 0 less than or equal to F, where F is theta with F greater than or equal on interior of D and F equal phi here, the boundary. So it looks like something like this. This is B. And then on each slice foliating B. So on ds, which is equal to B equals S of W, give germ of graph of S of V, subset of D times R. These are related to these previous B sub k's by this following proposition that basically any semi-contact regular B sub dominates some B sub k, theta sub k, or k. Alright, so I'm going to skip the proof of this and just go on to how you can do the proof. It's not, there's no the main idea is basically this regularity condition lets you, so just summarize the idea. That's one. You see, so as a map, phi is a map, basically from the disk by its foliation times interval as a time-dependent contact Hamiltonian on this star-shaped domain. So in which, once you have a contact Hamiltonian on a star-shaped domain type cross interval, then you're pretty close to considering Hamiltonian on star-shaped domain process 1. So now what I want to start, the main part is how these saucer shapes can be used to start trying to prove proposition 3.1. So the first step is just prove the following proposition. And it's that it's the same, it's proposition 3.1, but now instead of B sub k you have just some saucers. So up to O B, any almost contact has the form is such that 1, this is genuine complement of finite number of saucers, and 2 on each saucer is equivalent to semi-contact regular saucer. Right, so any of our almost contact structures, we can homotop it so that the air is a finite number of things, where it does speak of contact with a finite number of things, and they're all of this form. Okay, so step 1. So this is what I sketched last time. So